Hello everyone, welcome back to Chapter 9, Electrons and Atoms. In this little video we're going to practice the skills that we learned in previous segments about determining the electron configuration for particular atoms in the periodic table. And we said that electron configurations come from solutions from the quantum mechanical model of the atom. That's a fancy way of saying that we can explain where an electron is in an atom by a region of space called an orbital, and an orbital can be designated by a number and a letter. And that number is the principal quantum number. The letter, either S, P, D, or F, that says something about the shape of the region of space that electron occupies. We can determine that orbital number and letter from trends in the periodic table. So hopefully you have from the previous video your periodic table in front of you. If not, you can use this one I have in the slide that shows you in these little yellow boxes the trends that we use to determine the orbital number and letter for particular atoms. Okay. So we're going to mainly deal with these two transition metals to practice our skills in determining electron configurations for atoms. And I said in a previous video we're not going to deal with these in purple down here. But let's use the skills that we've talked about to give the electron configurations for these two elements. So let's start with Se, selenium. If I asked for the electron configuration for selenium, I look at my periodic table here and I see that selenium's right here in the periodic table, it has 34 electrons. A neutral element of Se has 34 electrons because it has 34 protons as well. So my electron configuration needs to give a home for 34 electrons. So one way I can check to make sure that my electron configuration is correct is to add up the superscripts of my electron configuration and make sure they equal 34. But to place those 34 electrons in their particular orbitals, I got to start from the very beginning here because I got to start with electron number 1, like with hydrogen. So I'm going to start with my 1s orbital. And my 1s orbital can have 2 electrons in it. So I'm going to start with 1s2 as my electron configuration. So if I was to stop there, that would just be helium. I can only stop when I get to 34. So I'm at 1s2. I have to go back over to number 3 here, lithium, and start placing electrons there. So 2s2, that 2s orbital can have 2 electrons. Then I'm going to travel over. Still got more electrons to place. I'm going to travel over here to boron. I am now at the 2p's. And how many electrons am I going to place in the 2p orbitals? I'm going to place 1, 2, 3, 4, 5, 6. So 2p6 is the next part of my electron configuration. If I was to stop there, that would be neon. Got to get to selenium, so I'm going to go back over number 11, sodium. I'm at the 3 s's, and I'm going to place 1, 2 electrons in the 3s orbital. Then I'm going to travel all the way over here, start placing electrons in these orbitals. I have to do that before I can even get, to get closer to selenium. I'm going to place 6 electrons in my 3p orbital. If I was to stop there, that would give me the electron configuration for argon. So I got to keep going. Travel over here to the 4s. I'll place 2 electrons in my 4s orbital. Now I'm at the transition metals. I'm at Sc, scandium, I gotta place electrons in all these orbitals first before I get to SE. So that means I'm going to be using my 3D orbitals. And how many electrons will I place in the 3D orbitals? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 electrons in those 3D orbitals. If I was to stop there, this would give me the electron configuration up here for zinc. Gotta place 4 more electrons to get to selenium. I have to place 1, 2, 3, 4 more electrons, and those 4 electrons are going to be in the 4p orbital. Once I place those 4 electrons, I am now at selenium. So I can stop because that's the element that I'm interested in. And to make sure I have placed all of my electrons, you can then go ahead and add up these superscripts, and they should add up to the number of electrons that your element has, which in this case is 34 for selenium. So that would be the electron configuration for selenium. And what this tells us is basically this tells us the home, or the orbitals, the regions of space where electrons in selenium lie. Okay. So let's do one more example with Y. Why? Because it's fun. I know you guys really miss my humor. So let's do the electron configuration for Y, which has how many electrons? It has 39 electrons. So 39 electrons need a home. So you can see that my electron configuration for Y, it's got to start exactly the same because we got to start placing electrons in lower energy orbitals first. So my electron configuration is going to start out exactly the same as it was with selenium. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. 3d10 gets me to zinc. Remember, I got to get to 39 here, so I now need to go 4p, 1, 2, 3, 4, 5, 6. So I have 6 electrons in my 4p orbital. If I was to stop there, that would give me the electron configuration for krypton, Kr. But I got to get to Y, tritium, so I need to come back to my 5s orbitals, and I need to place 1, 2 electrons in the 5s orbital. That would give me strontium, but I got to get to Y, so I have 1 more electron to place, and that 1 electron is going to go in the 4d orbital. So the last part of my electron configuration is going to be 4d1. If you want to convince yourself that you can stop, you can add up all these superscripts, and they should add up to 39. So this is the electron configuration for Y. So one more note that I want to make, and I usually make a bigger deal about this if we have more time in lecture, certainly if we were face-to-face. So all of the rules that we have talked about in doing electron configurations, all of those rules you're going to use to give electron configurations, but just like there is in chemistry, there are a few exceptions. There are a few transition metals that, following these rules that are sort of listed here on the periodic table with regards to trends, there are a few transition metals that break those rules. Now, I usually mention those in intro chem, but just due to the amount of material we still need to cover and such, we're not going to talk about those. So all of the electron configurations that we will do in this course will use the rules that we have talked about so far, and that we have talked about in writing those configurations. I'm not going to ask you to give me the electron configuration for a transition metal that's an exception. Okay, this Y transition metal is not an exception. Okay, So I just want you to know that these rules, these trends for writing electron configurations for elements work most of the time. There are a few exceptions where they do not work, but you will not be tested, nor will you be expected to know those exceptions.